little disappointed. The reason is because the majority of you solved it the same way. It kind of seems logical in a simplistic manner, but we went over this. There was a homework problem just like this. There was a handout like this that went over on the board. So apparently my teaching was deficient in this area. So we'll go over this one too again. I think the difficult part is there's the vectors, but then you had to do some algebra 2 work. Maybe it's actually algebra 1 work. 2 equations and 2 unknowns. And I guess people just didn't get that. So, all right. Are there questions? Anyone want to specify a question? Yes?
11B, specifically the math report.
Why don't I just go over 11?
Yeah.
All right. So 11A, well, the problem says that an airplane's going north. And by the way, I tried to take great pains if you gave me a direction either way, either, you know, the regular way we use, you know, angles, or the way avionics would use them. I think I caught all the possible answers, so if you used another strategy, that was okay. I just wanted you to know how to do it. So we're going north, and we travel 200 miles. This is part A. And you're going at 120 miles per hour. Well, you divide and you get 20 over 12, or 10 over 6, or 5/3 hours, which you can multiply by 60 and get 100 minutes, or 1 hour and 40 minutes. Any of those things were fine. 1.67 hours. Okay. No wind. You go straight. Fine. Okay. That's part A. Part B says you've got the same situation, but now you're going this way at 120 miles per hour. That's the velocity vector. And there's a wind going west. That's 90-degree angle at 60 miles per hour. What is the, so what do you do with these vectors? You're going to add them, right? Right, so graphically, the sum, right, you know, tail to head, tail to head. This is a new vector graphically. What is its magnitude? Well, Pythagorean theorem, square root of 60 squared plus 120 squared, whatever that comes out to be. 134 miles per hour. Okay, now what about the angle? Well, there's a few different ways you might have presented this to me, but you want to find this angle here, right? So what trig function is going to relate this angle to these two?
Sine? No, tangent.
No, because you don't know the... I mean, actually, if you find this first and put it over here, you could use the sine or the cosine. But just using these numbers, it's the tangent, right? This is the opposite over the adjacent, so it's the, we'll call that theta. Tangent of theta is 60 over 120, or a half. So whatever the inverse tangent of a half is, that tells you what this angle is. But actually, you should add 90 to it, right? And that would give you about 116.6 degrees, approximately. Or if you were like an aviator and you're measuring around this way, it's just 360 minus that angle, or 334. So those were the better answers. I didn't have to look too carefully. If I saw one of these numbers, I figured you figured it out. Okay, that's B. Part C says the pilot you know, we're going progressively. The pilot does not correct its course, but travels for 1 hour. He's traveling 1 hour. So, okay. This is where you originally went. It took, you know, 5/3 of an hour. But instead, I'm just going to write 60, 120 here. I don't want to confuse things. This is like a distance vector, and these are velocity, but this tells me the direction. I know the magnitude of this, but actually, it's actually easier to do this in components. Come on up, Alex. Anybody gets a little hungry, have a cookie. Okay. All right. So the easiest thing to do is to figure, well, after an hour, if you're going 120 miles an hour, you've traveled in this direction 120 miles. But if you've traveled an hour in this direction, you've traveled 60 miles. Right? And the whole thing was 200, so what's left up here is 80 miles. And C says, how far will the plane be from its original direct destination? So it's just this distance here, which you can find using Pythagorean theorem, square root of 60 miles squared plus 80 miles squared. That turns out to be 100 miles. Okay. Now, part D, which I admit must have been really confusing because hardly anybody figured out what I was asking. Some people did, and I gave them extra credit. If the wind stops after flying the original amount of time. Now, at least one person did a mistake that I actually, when I first did the problem, I made a mistake. I thought maybe you meant original, you meant like an hour. But no, that's, I mean, I gave you credit for that. I can't. If I can be fooled, you can be fooled. No, it's this amount of time, 5/3 of an hour. So this is so simple. He's traveling 120 miles an hour for 5/3 of an hour, so he gets this far in this direction. In this direction, he's traveling 60 miles an hour. He's somewhere over here. And what I asked was, what direction does he have to go? You know, the wind stopped now. Actually, it doesn't matter. The wind doesn't matter if the wind stops. But what direction will he have to go to get to its original destination? Well, obviously east. Or 90 degrees. Or 0 degrees. Well, 90 degrees or 0 degrees. So it's a really easy question, but obviously it was confused the hell out of me. So that's part D. Okay. Other questions? Everybody happy with your problems? Well, nobody's going to say anything. I'm going to.
So just I get confused, like, there's no mathematics, it's just conceptual answer?
Well, I mean, you can do some computation here. You can think of it this way. Let's say this is 0, 0. Let's say that's the origin, right? So the original, you know, the destination is clearly at 0, 200. If you travel the original distance with the wind, all right, now you're at this direction 200, and 5/3 hours times 60 is 100 miles. You're 100 miles away, right? So what's the direction from 100, 200 to 0, 200? I mean, it's 0 degrees. I mean, it's not, I mean, you can answer conceptually. You can just look at it and see that, but you can compute it too. Okay, I don't care. I think I heard someone say 12, and I'm not going to spend a lot of time on this. I'm just going to point out what I I know I pointed out before. You have a balloon, 1,000 pounds going up, right? So you have to be, the force vector down has to be 1,000. Your cables are kind of like this and like this. You know the sum of the force on this cable down plus the sum of the force on this cable down has to be 1,000, or it would go up or pull down if it's more. But almost everybody made this incorrect assumption that the force is split between these two cables going down. Exactly. That was nice. Nice and simple. But if this is 500 for this cable and 500 for this cable, then the force vectors here and here will not cancel. And the balloon will move one direction or another. Now, okay, I thought better of this. This is kind of a physics question. And since most of you showed me you understood how to manipulate vectors, I gave you most of the credit. If you realize that that's the other way to do the problem, I gave you most of the credit even if you got the wrong answer, because I was so impressed. Very few people did that. Okay, so how do you figure this out? Well, again, if you give this the label F1 and this the label F2, well, let me break it up. So this is F1, and it's made up of two vectors, this and this. We know this angle is 30 degrees. So this part here is what? Let's call it y, because that would be better. Y over F1 is what?
Sine of 30.
Sine of 30 degrees. So y is F1 sine of 30 degrees. Similarly, for this vector here, for this cable, right, it's pulling this way and this way. Here it's 45 degrees, this is F2. So what's this here? Well, you can just look at this. It's a isosceles right triangle. It's just going to be, this y is going to be F2 over the square root of 2. So that gives us our first equation, which is F2 over the square root of 2 has to equal F2 over the square root of 2 plus F1 sine 30. What's the sine of 30?
1 over 2.
Square root of 3 over 2. And that has to equal 1,000 pounds. Notice the sum of this pulling down and this pulling down, part coming from each cable, has to be 1,000. So that's one equation in two unknowns. The other equation is that this vector and this vector, you know what, I did that wrong. It's not. The sine of 30 degrees is a half. Yeah. Okay. Better. I think I did it wrong. If you think you got the right answer and I marked it wrong, you better check with me. Say, I did it too fast. Oh, no, I did it right. Never mind. Okay, the other equation, again, equates this vector and this vector. They have to cancel each other so the balloon doesn't move. So what's this vector here? Okay, if this one is F1 sine of 30, it's going to be F1 cosine of 30. And this guy over here, well, that's the same, right? It was a 45-degree angle, so that has to equal F2 over the square root of 2. So I have two equations and two unknowns. I can calculate F1 and F2 using my Algebra 1 right?
That'd be algebra 2,
No, I taught algebra 1. We did 2 equations and 2 unknowns.
but, well,
Yeah, we did quadratics in algebra 2, quadratic formula.
okay, well, I didn't do well in either
Okay,
one.
all right, all right. Okay. Any other questions? No other questions? Okay.
What was the final answer?
The final answers were, assuming I labeled these right, F1 was about 732 pounds, and F2 was 896 pounds. I mean, F2 over square root of 2, you can just substitute, right? You can just plug in F1 cosine 30 into here. Remove F1, divide by whatever, and divide 1,000 by whatever, you know. That's how you do it. Exercise for homework. Yes?
Wait, what did you say the answer was for 11C again? Is that what
11, which?
11C?
C was 100. I think that's still on the board here. Yeah. 60, 80, 3, 4, 5 right triangle.
Oh,
That's that other triangle. Okay, we're good? Yes?
But I still don't get it because, like, F1 and F2, like, if you said it's 1,000 pounds down, right? Why is it, like, when you add F1, F2, it doesn't equal 1,000 pounds? I don't understand that part.
Okay, let's look at this. You've got 2 guy wires.
Yeah.
The tension or the force on them is what we're trying to calculate, right?
Mhm.
We're pulling, one guy's pulling this way, another guy's pulling this way,
Yeah.
right? That force he's pulling has 2 components. He's pulling this way at a certain amount and straight down a certain amount,
Oh,
right?
okay. Yeah.
So this guy, the component of his force that's pulling down, plus the component of this guy who's pulling down, has to total 1,000.
Okay.
But they don't have to be equal.
Mhm.
In fact, they can't be, because we're at different angles. The component this way and this way have to be equal. But if the part going down was equal, the parts going this way wouldn't be.
Yeah.
I'd be pulling harder and the balloon would be moving.
Okay.
So, okay. All right. I must make a phone call. If we're done, I ask you kindly to put the quiz away and to not discuss it with your classmate who's going to return in just a second. Okay? It's Mitchell. Come on back. Okay? All right. Today, we are going to continue our adventure into identities. Sydney, I don't want to pick on you. Will you hand these out? If you didn't get the handout from yesterday, you're going to want to pick that up too. You're going to look at that too. You know, Cindy, I need more. So, we've talked about some identities so far, and they fit into a few different categories. The first category is what the book is calling primary identities. I'm calling these definitions. And they're all familiar to you. They're things like tangent theta equals sine theta over cosine theta. By now, you should know these like the back of your hand. You can see those on the first line. The second category is the odd-even identities. As an example, the sine of minus theta equals minus the sine of theta, because sine is an odd function. And I guess I should be clear, the cosine of minus theta is just equal to the cosine of theta, because theta is an even function. And you should be familiar with this, as well as the odd or evenness of the other basic trig functions, tangent, cotangent, secant, cosecant. We finished on Monday talking about the, I guess I should write here, odd, even. We finished on Monday talking about the co-function identities. Co in this case you can think of as complementary, right? Relationships between the angles that would be the smaller angles of a right triangle. For example, the sine of 90 degrees minus theta is equal to the cosine of theta. And you can switch the theta and the 90 minus theta. It works the same either way. And similarly, there are, because of this relationship, you can, if you took 1 over each of these, you'd find that 1 over the cosecant of 90 minus theta is 1 over the secant of theta. Again, these are the co-function identities. So that's as far as we got. We didn't really get to go over this worksheet, and that's fine, because we're gonna try and do as many examples today as possible. I'll let you guys have a chance to play with some of them. But before I do, I want to introduce one more family of identities. I kind of feel like they're the most important because this is a definition. This is very simple. It's not quite trivial. Again, this is also very simple, not quite trivial. This next family is a little broader in scope, and it just comes up over and over and over in mathematics. Some of you may be familiar with it already. It's generally these are referred to as Pythagorean identities, and you'll see why almost immediately. Before you see why, I'm just going to state why. Because they are equivalent to the Pythagorean theorem. You can use the Pythagorean theorem to prove these, and starting with the Pythagorean identity, you could prove the Pythagorean theorem. So let's see how that works. Question? No. Throat clear. Okay. It's a fine line, Okay. So what we're going to do is we're going to look at a right triangle. One of its smaller angles is theta. We're going to call the hypotenuse R. We'll call this leg Y and this leg X. Pretty straightforward. So we're going to first write down a description of the sine of theta. If this seems really simple, it is really simple. You just have to follow it through. Sine of theta is what? That's going to be y over r. Or as we're going to use it here, y equals r sine of theta. That should be familiar to you from both polar coordinates and somewhere else. All right. Cosine of theta is equal to x over r, or x equals r cosine theta. So now what we want to do is we want to write the Pythagorean theorem as it relates to this. The Pythagorean theorem says x squared plus y squared equals r squared. And now is the final, pretty much the final important step. I'm going to substitute in here for x and y into this equation. All right, let's try that. Here we have r squared cosine squared theta. Y is r sine theta, so r squared sine squared theta, and that's equal to r squared. But of course, we can divide by r squared, and we just have, I'm going to write it a little, I'm going to rearrange it. Sine squared plus theta plus cosine squared theta equals 1. Who here was familiar with this beforehand? Anyone? A few of you. Okay, you've seen it. All right. This is the primary way we think of the Pythagorean identity. It's really useful, and let me write that up here. Sine squared theta plus cosine squared theta equals 1. Now, I said there was a family of identities. I'm going to show you something related in a minute, but I also, before we go there, it's good to be familiar with this in a few different forms, because it comes up a lot, and it has a lot of useful purposes. So the first two forms I want to point out are very simple. If I subtract sine squared from both sides, I'm going to get cosine squared equals 1 minus sine squared. That's one useful form. And symmetrically, sine squared equals 1 minus cosine squared. But we can take these one step further. We can solve for cosine or sine here. I hope I'm not confusing anyone by not writing theta each time. Just taking a little time here. I can say cosine of theta equals the square root of 1 minus sine squared. Actually, we introduced an extra solution here. It's actually plus or minus depending. And likewise, sine is equal to plus or minus square root of 1 minus cosine. Now, the reason I gave you these two forms is because sometimes you won't see this, but you will see one of these. And you go, aha, 1 minus sine squared, I can simplify that. 1 minus cosine squared, I can simplify that. The reason these are really useful is sometimes you have an expression with sines and cosines. How did we get there? Well, you had tangents and cotangents, and you followed my advice from Monday and you converted everything to sines and cosines. But now you have a sine and a cosine and you want to get rid of one. Well, this turns a cosine into a sine or a sine into a cosine. So given an expression with trig functions, we can almost always, get it down to where there's just one function in there. And that's going to help us in some problems.
Can you go, can you pull the board up?
I'll give you a minute. Okay. So, I just want to leave this here. I won't stretch anyone's eyesight if I come up or use this board, will I? So there's a couple other members of this family that you can get very easily. All right, let me show you how you do that. If I have sine squared plus cosine squared equals 1, and if I divide by sine squared, well, this is 1. Cosine squared over sine squared. Cosine over sine squared. Cosine over sine is cotangent. And what is 1 over sine squared? That's 1 over the sine squared. Cosecant squared. Okay. Now, you might not recognize that right away as a Pythagorean identity, but it's part of the family, right? Okay, again, starting with sine squared plus cosine squared equals 1. This time, I'm going to divide by cosine squared. There, cosine squared. So now, sine over cosine squared, that's tangent squared, plus 1 equals secant squared. Okay, so here we have our happy family of Pythagorean identities. So maybe I should make a list of strategies here. I've given you one, which was convert to sines and cosines. Second, and maybe even more important, is look for a Pythagorean identity, and I'm going to throw in the word substitution. See if there's some place that the Pythagorean identity is going to help you solve this problem. Okay, let that sit for a second. I want to do a couple examples just to give you a feel for how this works. So we can put this up here. All right. So the first problem I want to show you is I want you to simplify the following. Simplify. 1 minus cosine squared theta times cotangent squared theta. See what we can do with this. So, following my advice, the first thing I'm going to do is make sure everything's a sine or a cosine. Cotangent is cosine over sine, so squared is cosine squared over sine squared. All right? Now I want to look for a Pythagorean identity. Does anyone see the Pythagorean identity I can substitute here?
Yeah, sine is square.
1 minus cosine.
Ah, 1 minus cosine. That's just sine squared. And clearly here I've got sine squared over sine squared. That's just usually 1. So the simplification is this becomes cosine squared theta. Okay, that was just a simplified problem. Let's try something that requests a little more of you. Questions about that? That seems straightforward, pretty simple, yeah. That's what this identity stuff, once you kind of get comfortable with it, they're fun, they're little puzzles, you know, you have to kind of work your way through. I was going to say fun, but I might offend some of you. Very idea, math could be fun. All right. Okay, this problem says, solve this equation. Cosine squared theta plus cosine squared theta tangent squared theta equals 2.6 cosine theta. Wow, that looks pretty intimidating, doesn't it? All right, let's don't panic. Let's first convert everything to sines and cosines. Tangent squared, that's sine squared theta over cosine squared theta equals 2.6 cosine theta. Okay, looks good. Cosine squared cancels, okay. All right, now what? Look at number 2 again. Look for a Pythagorean identity.
Cosine squared plus sine squared is 1.
Ah! Oh, that really helps. Okay, now all I have to do, cosine equals 1 over 2.6, and that, of course, brings us back to our calculator. So, I don't really want to pull the screens down and run this. I'm just going to inverse cosine of 1 divided by 2.6. I get 67.38 degrees. So if I plug 67.38 into this original equation, I expect it to work. All right. Let's do some problems. Why don't you try, let's try 1 and 2 on this, and ooh. Yeah, okay. Did anyone, I don't think anyone has this. This was yesterday's handout. When you're done with 1 and 2, come up and get this and just try the first 2 on here. I want to go over the 3rd and the 4th, but I want to do that together. I want to hold your hand on that a little bit. Okay? So work on those 2 for a few minutes. In other words, the one that says handout for lesson plan 17, it's got our table here with all the different identities, and just try number 1 and try number 2. They both ask you to simplify an expression.
So we first do this, right?
Yeah, do that one first, and then we're gonna backtrack a little. Oh, you know what? You know what, I wasn't looking at the right side. This one says lesson plan 16. When you're done with the first two, you can work on the first three on this also. They're pretty simple. Okay, I'll bring it over to you.
No, that's all right, there we go. You said 17, so I was coming up because I had 16 right here.
Oh, well, you didn't get 17.
You got 17 there?
I got 17. Oh, does everyone have 17 too? I got 17, 16. Who needs 17? Nope, okay.
All the identity chapters, like chapter 3.
Yeah,
I think it's all moderate.
but not necessarily in the order they do it.
But we're gonna do 2 now, like starting to.
We're kind of doing 2 today.
Okay.
We're not done.
No, I know.
I mean, I know you're overwhelmed with the fun we're having, but
No, not at all. I'm always pleasantly,
surprised.
yeah, I don't make judgments.
Okay. Does anyone here not get their Daisy, Dylan, Mohammed, Oscar, Philip, Ed, Vincent? I'm gonna erase a little there. Myself some room. You got it, right? Okay. Give him another couple minutes. I'm asking you to do the first 2 on 17, and then you could try the first 3 on 16. You might want to do them in the other order, because the 16 ones are easier. But 17. Okay. Okay, we're gonna go over them. So, don't worry.
Okay.
It's okay. All right, I think about a third of you are done and about a third of you maybe a little confused and a third of you are somewhere in the middle. Let me tell you something a little bit about doing these identities. The only way to really learn this is to do a lot of them. So we're going to go over some of these, but if you didn't get it already, watch and then take these sheets home and work on these. And then, when you're done with that, there is a homework assignment where it's a little longer than usual because practice is what's going to make you familiar with this. You know, it's not like weightlifting, but you know. Okay. Let me just start with this one.
This one, I think.
Yeah.
2 minutes.
I thought you were like doing beyond everybody else. You're like finishing the sheet, right? I'm going to give you a chance
Okay.
to do more. Okay. Let's just take a look at the first one on 16. I think should be pretty simple, especially if you follow step 1. Simplify tangent of x times cosecant of x times secant of x. All right? Tangent is sine over cosine. I think when you're doing these, shorthand is fine, right? Don't really, it's all the same variable, right? Cosecant is 1 over sine. Secant is 1 over cosine. So I get to simplify the signs out. This is 1 over cosine squared, and we could leave it that way, or maybe we could call this instead of 1 over the cosine, that's the secant squared of x. You can do algebra, you can do this. Are there any questions about the other two? Do we want me to do the other two on this page? Because I think they're equally as simple. Okay. let me skip ahead to number 1 on the 17. Secant squared theta times 1 minus sine squared theta. I want to simplify this. Well, secant squared is
4 cosine squared.
1 over cosine squared. And 1 minus sine squared, that's our Pythagorean, right? Cosine squared theta. So this is just going to generally equal 1. Anybody get anything different? Because sometimes I make mistakes. All right. All right. Let's number 2. Secant squared theta minus 1 over sine squared theta. Well, I hope you're good with fractions, right? How to run your fractions. 1 over, secant squared is 1 over cosine squared minus 1 over sine squared. Okay, we want to simplify our fraction here a little. This becomes 1 minus cosine squared theta over cosine squared theta. See, I don't actually do these before class. I just assume I'm smart enough to figure them out, but sometimes I have trouble with them. Okay, so, and then, you know, sine squared shows up here. Okay. Oh, I didn't follow my own advice.
Yes.
Sine
Yeah, you
squared.
can just make it like,
Second,
I just, now I want
Make it sine squared.
to, yeah, make it sine squared. Yeah. You know, and that goes away, and it becomes secant squared again. Yeah, okay. I should say this. I mean, you know, this strategy I give you here, I hate to use this word, it's kind of a scaffolding. But, you know, something to try when you're starting, if you don't know where to go. Just follow the steps, see if that gets you somewhere. If it doesn't, then you want to think about it. But eventually you get to where you just look and you kind of intuitively go, aha, I know what that smells like. It smells like easy. Okay. Questions about those two? Okay. Let's see, 3 on 16 is no, on 17. It's kind of the same idea. There's kind of a more advanced problem we're going to come across, but not in this section. All right. Why don't we take a break? 10, 15 minutes?
there's more
You can
material?
continue to work on these if you wish.
There's more material we can cover?
8 o'clock. This is a 2-hour class. We have a little bit more here. We have a little bit more to cover.
I think we'll go
You have to walk around.
one more.
Have a cookie. Have another.
Yeah.
Oh, class is
Elimination.
Yes, she's home. She's home.
I thought this was a harder problem. It's so easy. I want a harder problem, but I don't think I have one for you today. Anybody want to go up and do this for the class?
Yes?
Okay. Fight it out amongst yourselves.
You wanna go?
They both want to go. Flip a coin.
No, go ahead.
Put
I'm
the
shy.
cookie.
No, it's okay. No, I'm shy. Okay. I'm afraid of stage.
Oh, then you must.
Then you must.
Then you must, yes. It's a learning experience, come on.
Please, yeah, go.
Everybody, I won't make you, but
Okay. I will go.
it's intimidating because
It
English
is.
isn't your first language, right?
Huh?
English isn't your first language?
Yeah.
All right, so,
Okay.
all right, and before you start, everybody clap a little. They love you.
Go ahead. Okay.
Go ahead.
So this is a formula. I mean,
It's an equation.
Equation, yeah. So should I take a marker and write down the solution?
Well, you want to solve it. Show us how you solve
Okay, okay. So my handwriting is not so excellent.
it. Yeah, it's much better than mine, so.
So this is our formula. I mean, our identity. It's not a formula. It's an identity to be right. Here. So we can move this to that side, right? So -1 - 2 is -3. And so then we can just, how to say,
Simplify.
simplify that. Yes. Thank you. So this is 1 over cosine cosine theta, right? Here, correct? Correct? Thank you. And then it's -3. And then we move everything on that side. So it's cosine of theta -1/3.
Would you like a calculator?
No, I solved it.
All right.
Yes, I have
Okay, go
I
ahead.
have a cheat sheet. And then, so this is inverse of that. I will write it down. I want to be detailed. And then calculator gives me 109 and 47 degrees.
Okay. Very good, thank you. Now, I want to point out something that turns out not to be important for this example, but something you should watch out for. All right? Suppose, see, we know that 109 degrees is, the solution to this. But one thing you might want to watch out for is it the solution to this? In this case, there's no problem, right? But what kind of problems could you run into? Well, if, for example, if you ended up with a solution pi over 2, right? You get 1 minus sine squared pi over 2. Well, sine squared pi over 2 is 1. You get 0, and it wouldn't be a solution. It'd be like an extraneous root. Does everyone remember extraneous roots? If somewhere in this process you found a square root, or you squared something, you sometimes get extraneous roots that way. So you do want to be a little careful. It doesn't hurt to plug it back in and make sure it works. Also, we didn't specify in this example, so what you did is fine, but if I said find all solutions, right, you might think, oh, well, these are periodic, just like we did at the beginning of class. So you can plus 360n. That's just something to think about. Okay, very good, very good. What do I want to do next? I'll tell you what I want. Here's what I want. I have a little bit more to say about identities today, maybe about 10 minutes worth. I'd really like you guys to take these, and if we went over one but you didn't get it, try it until you get it. If we didn't go over it, try it and bring it in on next Monday, and definitely do the homework. Definitely do the homework, struggle with it, come in with questions, practice it, because this stuff is going to be like riding a bicycle. Once you get it, it'll be easy. But if you don't, and you come in for the quiz, you're going to go, oh my gosh, what do I do? Because there's no algorithm for solving these. This is, it's a framework, but you're gonna have to have a little experience, and once you have that, you'll be brave and you'll be able to solve all of these. Okay? Before I go on, any other questions about this? Okay.
No, I have a question, like the practice 16.
Practice 16.
No, I mean
Yeah,
the
16.
handout 16.
Yes, yes.
And then
Number.
find the solution over 0 and 360. And then
Where's that? Oh, 16, I'm sorry, I got the wrong one. Find the solution over 0 to 360, yeah.
yeah, that worked the first one.
Let me go through that. Okay,
Is it like there's two solutions or just the one solution?
I don't know. So this problem is specific about the domain, limiting the domain it wants the answer in, right?
Yeah.
So it says negative 3.95 equals secant of minus x minus 2. Okay, well, the first thing, let me go ahead and change this to a 1 over the cosine of minus x, right? Minus 2 equals negative 3.95. And then, of course, I want to invoke my odd-even identity here. Cosine is, everybody knows, even. So this is just negative 3.95 equals 1 over the cosine of minus x minus 2. I want to move this to the other side. I just add 2 to both sides. So I get negative 1.95 equals 1 over the, forgot to take it out, cosine of x. And then I can find the reciprocal of both sides, right? And I get cosine of x equals negative 1 over 1.95. Okay, so now I want to get the primary solution. So let's pull out my calculator here. So inverse cosine 1, inverse cosine minus 1 divided by 1.95. I get 120.9, let's say. Right. Let's take a reminder look of our unit circle. The cosine here, that's the x coordinate is 120.
Well, Professor?
Yeah.
I think x is minus, so it's minus 120, so it's going to be down, it's not up.
Yeah, you lost the
It's,
minus.
Yeah.
Yeah, I'm tired. Hold on, let me think hard, because I
That's
don't want to
okay.
agree with you until I agree with you.
It will
So-
be the same, but
So this is cosine of x, sine of x, right? So isn't that it? Yeah.
No. What I'm saying, cosine of x, if you look to the equation back at the beginning, you will see minus x. The angle is minus x. So you didn't change it. So it's minus 120.9, not 120.
So between your second and third line, you forgot the minus.
No, I didn't.
So you're on your
I
second.
removed it intentionally.
Because it's
Why did I
even.
remove it?
Because
I
it's
guess I didn't
even
say that
function.
clearly.
Even.
Why can I remove that minus x?
Because it doesn't matter because cosine is
Because it's an
odd.
even function.
Even.
Okay, okay. Odd even identities. Sine of negative theta is negative sine of theta. It's an odd function. Cosine of minus theta is just cosine of theta. It's an even function.
Okay.
All right. If I were doing a proof, you know, I'd have to say, well, substitution here, and then, you know, identity, even cosine or something. So, as it turns out, it doesn't matter if you don't do that, right? Because what I would get is it's minus 120. Well, minus 120 is not between 0 and 360, but minus 120 is down here, right? And I need this solution, right? Between 0 and 360, this is, I'm just going to forget the 0.9 to make it simple, right? I would have to add 360, right, which would be 240 degrees. That's this angle, right? So as soon as I get either one of these, either 120 or 240, I can see that to get all the solutions between 0 and 360, I have to get both these points here, or both these angles here. This is really something we did earlier in the class, and you have to remember it now. Can't forget it. We're just adding in this new feature of we're using these identities to simplify. All right, but at the beginning of the class, I just said this on this, you should be able to do this. Are we okay with that? Because, all right. Other questions on these problems before we go forward? Okay. So what we've done is we've done some simplifying of expressions. We've done some simplifying of expressions in an equation and solving the equation. One of the next thing we're going to be doing is which is basically the same type of stuff, but we're going to be a little more formal. We're going to verify identities. Now, I think I mentioned on Monday that verifying an identity is a little like a proof. In fact, that's exactly what it is. And I think I mentioned that sometimes you can just show one set of steps. You can go from A to B. And if the steps are reversible, you don't have to worry about going from B to A. Let me back up a little. When I say some expression A is equal to B, right? The way we say this in mathematics, well, I mean, you could just say that. That's one way to write it. Another way to say it would be say, if A, then B. But in the case of equality and identity, it's also, you have to show if B, then A. So, on Monday I pointed out that, well, sometimes when you go from A to B, you can just finish your proof by saying, and the steps are all reversible, right? But one thing you want to be very careful that you don't do is you don't start out assuming A equals B and then just say, you see, I got something okay when I did that. And I'm going to show you what I mean by that. I'm going to show you how to not do an identity proof. All right? So the identity I want to show is that sine of theta over 1 minus cosine theta equals 1 plus cosine theta over sine theta. All right, I want to show that this is correct. So here's how I'm going to do it incorrectly. All right, if A over B equals C over D, then I can cross multiply, right? So I'm going to say sine times sine, that's sine squared theta, equals 1 minus cosine times 1 plus cosine. That's a minus b times a plus b, which is just
1 squared.
a squared minus b squared, yeah. Minus cosine squared. But that's just sine squared. So that's good, right? What's wrong with this argument is I started by assuming this was true. Now, in this case, this actually is a valid identity. That there are circumstances where you can start by assuming something is true and show it's true, but it's not. So what's the formal way to do this, right? What's the right way to do this, to show this? Let's start over. We want to show that sine of theta over 1 minus cosine of theta. I'm going to put a little question mark here. We don't know this. That's what we want to show. It's equal to 1 plus cosine theta over sine theta. So how to go about doing this? Well, I'm not gonna say how I figured this out yet. We'll get to that in a second. But I'm gonna say, I'm gonna multiply this by 1, right? I'm gonna multiply sine theta over 1 minus cosine theta. I'm gonna multiply that by 1 plus cosine theta over 1 plus cosine theta. We would all agree that this is usually 1, and I can multiply something by 1 without changing it. Right? It's the identity property. Okay, so what do I get here? I get sine theta plus sine theta cosine theta, and that's over 1 minus cosine squared theta. That's good. Now I'm going to use my Pythagorean identity here. You can draw arrows like this. So now I have sine theta plus sine theta cosine theta over sine squared theta. And now I'm going to reduce, I'm going to divide out a factor of sine theta from both sides, from the top and the bottom. So I get 1 plus cosine theta over sine theta. Well, that's what I wanted to show, right? And furthermore, my steps are reversible. So now I've shown that this equals this, and this equals this. And I've done it properly. Yes?
How did you realize that you need to multiply by the 1 plus cosine theta?
Okay, that's exactly what I want to talk about, right? How you figure this out, that doesn't have to be done formally, correct? In other words, you can cheat, right? You can do kind of a cross multiply here if you want to see, oh yeah, it kind of worked out, and then figure out how to get from A to B, right? I'm going to give you. I think I'm going to try and show you a strategy to do just that, to figure it out. Right? One strategy is to start on one side. Where am I? Sine theta over minus cosine theta. Start over here, and we'll start over here. Sine theta. And I'm going to work down until I get the same thing. So I look at this and I say, well, the denominator here, I've got cosine, 1 minus cosine, and I have a sine over there. So I need to get the denominator to be sines, right? So how can I do that? Well,
We needed to make it a square somehow.
well, I mean, unfortunately, the obvious thing is, you know, what you're asking, how do I figure out is the obvious? If you multiply it by 1 plus cosine theta, it's going to become sine squared theta, right? You see that?
Right.
This is why this Pythagorean substitution is so important. It just comes up all the time. So let's try that. Let's multiply this by 1 plus cosine theta, and this times 1 plus cosine theta. And we get sine theta times 1 plus cosine theta over sine squared theta. Okay. Well, then I might come over here and I might go, well, that's a sine squared. I have to multiply both sides, the top and the bottom, by sine now, right? Sine theta times 1 plus cosine theta over sine theta. Okay. Am I there yet? Yes, right? I worked this down and I worked this down, and they're equal. Now, to make this into a formal proof, you can, I mean, you can kind of skip a step here. We say, well, I can go from here to here, I can go from here to here, and again, my steps are reversible. Usually, it might not be that easy. You might have to take many steps down to here and many down to here. And then, if you want to look a little more obscure and a little more brilliant, then you would rewrite the whole thing on another piece of paper and just go A, B, C, D, E, F, G, H, and the steps are reversible. I know this sounds a little picayune, but this is the way we would do a proof. Right? So, okay, let's see. Let's see another example. Again, the subject matter here is how to verify an identity. All right. The identity I want to verify here is cosecant theta tangent theta. And I'm again putting a question mark here because I don't want to assume this. This is just where I want to get to. Cosine theta secant squared theta. So I'm going to apply this process I talked about on both sides. First, I'm going to convert this to sines and cosines. By the way, it's not the only way to do it. You know, if you like, you know, tangent, secant, cosecant identities and you know them, you can do that. But when in doubt, if you're not quite sure, you know, step number 1, converting to sines and cosines is usually a good idea. So this is 1 over sine theta. Tangent is sine over cosine theta. Okay, I'm not going to write an equal sign because I don't know this. Here I have cosine theta. 1 over secant. Secant squared is 1 over
Cosine.
cosine squared. Thank you. Okay, let's see here. I can cross these out and get cosine theta. 1 over cosine theta. Here I eliminate a cosine. 1 over cosine theta. Oh, okay. So now these are equal. So now I know my pathway for the proof. I can convert this to this. I can convert this to this. This to this. Multiply, you know, top and bottom by cosine, and then convert to this. It just takes a little planning, that's all. Questions about this strategy?
Oh,
Yes?
this is not the final answer. You have to go through everything.
Well, you know, this is a way to think it through. If you wanted to do a really formal proof that doesn't really show how you got the answer, like the way when I first did this
Cross
problem up
multiply?
here, you could then say step A, B, C, D, E. You could do it that way. But you could also say, look, this is step A, step B, step C, and then, you know, not really say how I got it, but then, you know, these steps. And of course, you always want to indicate these steps are reversible because I want to get from here to here, and I want to get back. We're not mathematicians in this class, not yet. We're not publishing this for other mathematicians to rip apart. So we have some leeway. The only thing you want to be really careful about is not assuming the result, right? Because if you do, you can prove something that's not true. The formal way to say that, if A, then A is always a true statement. If A is true, if A, then A is true. If A is false, if A, then A is true. Right? So showing if A, then A, even if A, if and only if A, doesn't get you anywhere. I guess that's a little abstract, but that's, I guess, the way to say it. Yes, Jessica?
If we have to do this in like a quiz or something, and we do it the way you showed us, with like doing it halfway down one side and halfway down the
Yeah,
other.
I'm good. I'm good. Just you want to indicate, you know, like exactly the way I might have, like, you know, to draw an arrow. Say, this is the direction of the proof, and it's reversible, right? That's what you want to do. Okay.
You're gonna have some homework problems like this, right?
Sure hope so. There will be. We're not done with identities today. We're going to work on them also on Monday, and maybe a little even to the next class. There will be homework problems. I'd have to look it up. You want me to look it up? There will be problems like this on the homework. So I just don't know if it's in tonight's assignment. Actually, if you're really, I think both assignments are already. No, I don't think so. I'll try and put the second one up tonight. Okay, if there are any questions, you can ask them now or after class is over. I'm fine with ending class now. If you have other issues come up,